Okay, energy changes in chemical reactions. First question, we have to balance this equation, which is the equation for the combustion of methane, CH4. So, start on the left and let's see. First element is carbon, so there's one on the left and there's one on the right. So the carbons are currently balanced. So move along to the next one. Hydrogen, there's 4 on the left and there's 2 on the right. Okay, so let's try adding a 2 there to turn that into 4 hydrogens. Remember, with balancing equations, you're only allowed to add big numbers at the front. You're not allowed to change the little numbers. Okay, so now we've added a big number, reevaluate. There's 1 carbon on the left and right, so the carbons are fine. 4 hydrogens on the left, 2 times 2, 4 on the right, so they're balanced. So move along. Oxygens, there's 2 on the left, and there's currently 2 there and 4 there on the right. So we need to get 4 on the left. So we can do that by putting a big 2 there. And now it's balanced. 1 carbon, 1 carbon, 4 hydrogens, 2 times 2, 4 hydrogens, 2 times 2, 4 oxygens, 1, 2, 3, 4 oxygens on the right. And that's the balanced equation for the combustion of methane. Next question. Calculate the heat energy released by burning 0.8 grams of alcohol. Okay, so it's a Q equals MC delta T question. They've told us we've got 0.8 grams of alcohol that we've burnt and we're heating 50 grams of water. So the temperature change is 22 to 38.4, so therefore delta T is 38.4 minus 22. So delta T is 16.4 degrees. Okay. Now, they've given you C, that just leaves the M. They've given us 2 masses. Which one do you use? The 0.8 grams of alcohol is a red herring, okay? It's there just to try and trick you. With Q equals MC delta T questions, the mass, the M, it's always the mass of the water, okay? You don't need the 0.8 grams at all. So, put in the numbers, mass, 50 grams. In these questions, don't convert the mass into kilograms. Normally in science you do that, but look at the units of the specific heat capacity of water here, joules per gram. So leave it in grams. So mass is 50 grams, C is 4.2, and delta T is 16.4. Stick that in a calculator and you get 3,444. And the units, joules of course, because it's heat. Yep, that's it. 3,444 joules. Just remember, the mass is always the mass of the water, not the mass of anything else. Okay, next question. The combustion of ethanol. So, here it is. They've balanced it for us, which is nice of them. What are we going to do? Well, we have to use the bond energies to calculate the overall energy change. Right, so a bond energy question. So here are the chemical formulas of each of the reactants drawn out. So that's ethanol, that's oxygen, O double bonded to an O, and there's 3 of them, big 3 at the front. That's what the big 3 means. It means 3 O2 molecules, and that's what we've got. Carbon dioxide is C double bonded to an O on both sides, and that's water, which I'm sure you knew. So, what you have to do, these bond energy questions, is write down underneath how many of each different type of bond you've got. So, in the ethanol, we have, let's start with carbon-hydrogen bond, okay? We have 1, 2, 3, 4, 5 carbon-hydrogen bonds. Okay, so 5 CH bonds. We've also got 1 carbon-carbon bond, 1 carbon-carbon. We've got 1 carbon-oxygen bond, and we've got 1 oxygen-hydrogen bond. Okay? And that should add up to 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. Yeah, we've got all the bonds in the ethanol. Okay, here we have 3 oxygen double bonded to oxygens. That one there. So 3 O's. Okay? And on this side, we've got 1, 2, 3, 4 C double bonded to O. Okay? And here we have 1, 2, 3, 4, 5, 6 O bonded to H, single bond. Well, it has to be if it's an OH bond. Okay, so write it out like that. And then just stick in the numbers. So 5 CHs, CH bond has a bond energy of 413 kilojoules per mole. So that becomes 5 times 413 plus the CC is 347 plus CO 358 and an OH is I'm kind of interfering with this diagram, never mind. An OH is 467. Okay. Next, 3 OOs is 495. Okay. And that goes to, on this side, 4 COs. That's 4 times 799. And 6 OHs, which is 467. Okay? So, stick those numbers in the calculator and you get, if you add all of that up, okay, it comes to 4722. Okay, and stick that in the calculator and you get 5998. Okay, so what that means is that all the bond energies of the reactants adds up to that, kilojoules per mole, okay, and all of the products, the bond energies add up to that. So when this reaction happens, all these bonds are broken, so you have to put in that amount of energy, and when the reactants form, all these bonds are made, and that releases this amount of energy, and they're different. So when the bonds reform, more energy is released than is taken in breaking them, and therefore it's an exothermic reaction. So the question said calculate the overall energy change. So you just do 5998 minus 4722, which is 1276 kilojoules per mole. This pen's packing in. Okay, so that means, because it's an exothermic reaction, 1276 kilojoules per mole is released when this combustion reaction takes place. It's a combustion reaction. Combustion means burning. You're burning ethanol. And you know when you burn stuff, it releases heat. So if that number was smaller than that, you know you've done something wrong. Okay. There we go. That's the answer. Right, next question. Explain why this reaction is exothermic. I just did that in terms of bonds broken and bonds formed. I sort of half did that. Okay, it's exothermic. I've already told you why it's exothermic because that number's bigger than that. But to answer the question, to get the marks, you have to do it in terms of bonds broken and bonds formed. So, first thing, okay, say that the energy is taken in when bonds are broken. Okay, energy in to break bonds. Okay, then say the energy is released when they reform. Okay, so they're broken, on all these bonds are broken and they're reformed on this side. And finally, say, just to get it right, when more energy is released when bonds reform than when they're broken, overall energy is released, so it's exothermic. Okay? So use the term overall. It's always important in these sort of questions. So overall, when more energy from being reformed than when they're broken, then it's exothermic. I'll just read that out again. When more energy is released when bonds reform than when they're broken, overall energy is released, so it's exothermic. Good, okay. Final question, this thing. Complete the energy level diagram for the combustion of ethanol. Label the activation energy and the overall energy change. Right, so here is ethanol and the oxygen there. And somewhere here we're going to draw the carbon dioxide and the water. Overall, as we've discussed, it's an exothermic reaction. So the final line is going to be lower than that one down here somewhere. So let's put that in. Okay, that's going to be 2 carbon dioxides and 3 waters. Okay? Right. With these sort of diagrams, the energy goes up and then down. So draw them like so. Okay? What that means is that you have to put in a certain amount of energy. It's called the activation energy in order to get the reaction to take place. The reactants start off at this energy level and the products end up at this energy level, but you've got to get over this energy hump in order to get the reaction going. And that is called the activation energy. Okay? And you also have to label the overall energy change. Well, the overall change is from where you started to where you end up. So that's the overall energy change. Okay? And that's the energy level diagram. There we go.